Now, in this lecture, we will find the radius of the small circle. In the drawing, we have two circles with an interline lunge between them and this point. They touch each other at this point. Let's call this point point N. Again, these two circles have an internal lunge between them at this point, and we also know that AB is the diameter of the big circle, and also we know that AC equals to 9 units, BD equals to 4 units. This is a right angle, and this is also an angle of 90 degrees. Okay, and we want to find out the radius of this small circle. Okay, first of all, this angle is also a right angle because actually we have here right angle, so this angle must complete the sum of the angles on the upper side of the straight line to 130 degrees to 180 degrees, and we know that this angle equals to 90 degrees, so in order to complete the sum of the angles to 180 degrees, this angle must be equal to 90 degrees. And for the same reason, this is also a right angle. And we actually have three tangents to the small circle. This tangent is tangent to the circle at this point. So let's call this point point S, and this tangent is tangent to the circle at this point. Let's call this point point Z. Actually, point Z is the lunge point between the tangent to the circle and the circle itself, and also here point S is the lunge point between the circle and this tangent. And also we have the third tangent to the circle. This tangent is tangent to the circle at this point. Let's call this point point M, and again point M is the lunge point between this tangent and the circle. Okay, so in the next step we will define the center of the small circle. This is the center of the small circle. Let's define this point as point Q. Again, point Q is the center of the small circle, and we will define point P as the center of the big circle. Again, point P is the center of the big circle. Okay, so I will write it down. Q is the center of the small circle. Point Q is the center of the small circle, and point P is the center of the big circle. So I will read the things that I wrote. Point Q is the center of the small circle. This is the center of the small circle. And point P is the center of the big circle. Point P is the center of the big circle. Okay, this point P in the red color is the center of the big circle. And we will also define as small r. Small r is the radius of the small circle. And capital R is the radius of the big circle. So I will read again the things that I wrote. Small r is the radius of the small circle, and capital R is the radius of the big circle. Okay, so in the next step I will draw 3 radiuses of the small circle. Those radiuses will exit from the center of the circle and will touch the launch points of the circle. So the first radius starts from point Q and touches the circle at point S, that is the launch point. Okay, so this radius touches the launch point, that is point S. And we will draw the second radius that is also exit from the center of the circle and touches the launch point, point Z. Okay, the second radius also touches the launch point, that is point Z. The launch point between the tangent and the circle. And I will draw the third radius that exits from the center of the circle and touches the launch point, that is point M. Okay, so we have here 3 radiuses that are drawn to the launch points of the circle. Okay, so the next step we have actually a rule. I will call it rule number 1. So I will present you rule number 1. According to rule number 1, the tangent to the circle is perpendicular to the radius to the radius at the launch point. So I will read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, so actually the meaning of rule number 1 is that if you draw a radius that is drawn to the launch point, then this radius will be perpendicular to the tangent. For example, this radius is drawn to the launch point, actually it touches the launch point, that is point Z, therefore this radius is perpendicular to the tangent. This is a right angle. Okay, so whenever you draw a radius that is drawn to the launch point, that touches the launch point, then that radius will be perpendicular to the tangent. Also we have here radius that touches the launch point, it is drawn to the launch point, therefore the radius is perpendicular to its tangent. To say that the tangent is perpendicular to the radius, or the radius is perpendicular to the tangent, it is exactly the same thing. Okay, so when the rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point, it also can be said that the tangent to the circle, that the radius is perpendicular to the tangent. It is exactly the same thing. And also we have the third radius that is drawn to the launch point, that is point M, therefore that radius is perpendicular to the tangent. This is a right angle and this is also a right angle. Okay, so the next step we will focus on quadrilateral QZMD. Okay, on quadrilateral QZMD, quadrilateral QZMD has 3 right angles that the sum of them equals to 270 degrees. Okay, so quadrilateral QZMD has 3 right angles that the sum of them equals to 270 degrees, because 90 times 3 is 270 degrees. And we have a rule number 2. According to rule number 2, the sum of the angles inside a quadrilateral equals to 360 degrees. Okay, so I will read rule number 2 again. Rule number 2 states that the sum of the angles inside a quadrilateral equals to 360 degrees. So according to rule number 2, the sum of the angles in quadrilateral QZMD must be equal to 360 degrees. That is to say, the sum of the three angles that equals to 270 degrees plus the sum of the fourth angle must be equal to 360 degrees. So I will define the size of the fourth angle as y. Y is the size of the fourth angle in quadrilateral QZMD. Okay, according to our definition, y is the size of the fourth angle in quadrilateral QZMD. So actually, according to rule number 2, 270 degrees plus y must be equal to 360 degrees, because rule number 2 states that the sum of the four angles of the quadrilateral must be equal to 360 degrees. So the sum of the three angles, that is 270 degrees plus the size of the fourth angle, must be equal in total to 360 degrees. Okay, so here we will subtract 270 degrees from this equality, and we will get that y equals to 360 degrees minus 270 degrees. That is to say, y equals to 90 degrees. Okay, so we found out that y equals to 90 degrees. That is to say, this is also a right angle. So actually, we found out that quadrilateral QZMD has four right angles. Okay, this quadrilateral has four right angles. All of its inside angles are right angles. Okay, and we have rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. Okay, so rule number 3, read rule number 3 again. Rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. So, according to rule number 3, quadrilateral QZMD is a rectangle. Okay? Again, according to rule number 3, quadrilateral QZMD is a rectangle because it has 4 right angles. Okay? And we also have rule number 4, that states that the opposite sides of a rectangle are equal to each other. Okay, rule number 4 states that the opposite sides of a rectangle are equal to each other. So I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. So actually we found out that quadrilateral QZMD is a rectangle, and therefore, according to rule number 4, the opposite sides of quadrilateral QZMD are equal to each other. That is to say, QZ is equal to MD. QZ is equal to MD according to rule number 4 that states that the opposite sides of a rectangle are equal to each other. QZMD is a rectangle, so according to rule number 4, its opposite sides are equal to each other. Okay, according to rule number 4, QZ equals to MD. Okay, but we know that QZ is the radius of the small circle, so QZ equals to small r because it is the radius of the small circle. So we have here this equality, and we can derive from this equality that MD equals to R. Okay? we got that FD equals to R. MD equals to the radius of the small circle. MD equals to small r, that is the radius of the small circle. Okay? And we actually have also the quadrilateral SQCM exactly with the same. We will repeat on the same process in order to prove that CM also equals to small r. Actually, quadrilateral SQCM has 3 right angles, 1, 2, 3. So according to rule number 2, that the sum of the angles in a quadrilateral equals to 360 degrees, this angle must be equal to 90 degrees. So quadrilateral QSCM has 4 right angles. So according to rule number 3, quadrilateral QSCM is a rectangle. And we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. That is to say, QS equals to CM. But QS equals to small r, and CM equals to QS. So CM also must be equal to small r. Okay, so we got to the conclusion that CM also equals to the radius of the small circle, that is to say it equals to small r. Okay, and in the next step we will define PM as x, that is to say PM equals to x according to our definition. Okay, PM equals to x, and then what is the value of CP? The value of CP equals to CM. CP equals to CM minus PM. CP equals to CM minus PM. So actually CP equals to CM, that is small r, minus PM, that is x. So CP equals to r minus x. Okay, CP equals to r minus x. And in the next step, we will calculate the radius of the big circle in 2 different ways. We know that AB, that is the diameter of the big circle, equals to 2 times the radius of the big circle. So actually AP is the radius of the big circle, so that will be our first equation that states that AP equals to capital R. AP equals to capital R. AP equals to capital R because P is the center of the big circle, and also we have the second equation for the radius of the big circle that states that PB also equals to capital R. Okay, PB equals to capital R. Okay, we have the second equation that states that PB also equals to capital R. So we will return to our first equation that AP equals to capital R. But what is the size of AP? AP equals to AC plus CP. Again, AP equals to AC plus CP. Okay, AP equals to AC plus CP. You can see it from the drawing. But AP equals to 9 units according to what is given us in the question. AC equals to 9 units according to what is given us in the question. And we found out that CP equals to small r minus x. Okay, so we got this expression for the radius of the big circle. The radius of the big circle equals to 9 plus small r minus x. Okay, so I'll write it again. The radius of the small circle equals to 9 plus small r minus x. Okay, we got the first expression in the question for the radius of the big circle. The radius of the big circle equals to 9 plus small r minus x. And we have our first expression, our second expression, and the equation for the radius of the big circle that states that PB equals to capital R. Okay, PB equals to capital R. PB equals to capital R. But what is the size of PB? PB equals to PM plus MD plus DB. Again, PB equals to PM plus MD plus DB. From the drawing, we can see that PB equals to MD plus PB equals to PM plus MD plus DB. But what is the value of PM? PM equals to X equals to X according to our definition, and MD equals to small r. That is what we found out, that MD equals to small r, and DB equals to 4 units. It is given us in the question. So in total, we got the equality that states that PB equals to capital R equals to X plus small r plus 4. So I'll write again equation number 2 that states that capital R, that is the radius of the big circle, equals to X plus small r plus 4. That is the first equation and the second equation, and we have also the first equation for the radius of the big circle. Okay, so actually we have two equations for the radius of the big circle. So because we are talking about the same radius, of course that equation number 1 will be equal to equation number 2. So I will create the first equation that states that the radius of the big circle according to equation number 1 equals to the radius of the same big circle according to equation number 2. Okay, or capital R equals to capital R. Okay, so capital R according to equation number 1 is 9 plus small r minus x equals to capital R according to equation number 2, that is x plus small r plus 4. Again, equation number 3 states that capital R according to equation number 1 equals to capital R according to equation number 2. Okay, here we have R in this side of the equation and we have R on the other side of the equation. So we can cancel R. So what's left after we cancel R? What is left actually is 9 minus x equals to x plus 4. So actually that is what left after we cancelled r. 9 minus x equals to x plus 4. Here we will subtract 4 from this equality and we will get that nine minus 4 is 5. So we got that 5 minus x equals to x. Here we will add x to this equality and we will get that five minus x plus x is 5 equals to x plus x is 2x. Okay, we got this equality that states that 5 equals to 2x. Here we will divide this equality by 2 in order to get the value of x. Okay, so x equals to 5 over 2. 5 over 2 is 2.5 units. So, okay, so we found out the value of x. X equals to 2.5 units. So after we know the value of x, we can substitute x in equation number 1 by 2.5 units. We have equation number 1 that states that capital R equals to 9 plus small r minus x. This is equation number 1, that capital R equals to 9 plus r minus x. So here we will substitute in equation number 1 x by 2.5 units and we will get that capital R equals to 9 plus r minus 2.5. Okay, we got that capital R equals to 9 plus r minus 2.5. 9 minus 2.5 is 6.5. So in total we got that capital R equals to 6.5 plus r. Okay, so the expression for capital R is that capital R equals to 6.5 plus r, and we have already found out that x equals to 2.5 units. Okay. In the next step, I will present a new rule number 5, and we will implement rule number 5 in our two circles. So, according to rule number 5, Rule number 5 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. Rule number 5 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so the meaning of rule number 5 is that if two circles touch each other internally at a certain point, then the distance between their centers equals to the difference between their radiuses. So if the distance between their centers is D and R1 and R1 is the radius of the big circle and R2 is the radius of the small circle, then according to rule number 5, D equals to R1 minus R2. Okay, so we can implement rule number 5 in our circle. According to rule number 5, we have here two circles with an internal length between them at point N. They touch each other internally at point N. So we can implement rule number 5 in these two circles. And according to rule number 5, the distance between their centers, that is to say QP, because Q is the center of the small circle and P is the center of the big circle, so QP is the distance between their centers. So according to rule number 5, this distance between their centers, that is QP, equals to the difference between the lengths of their radiuses. So the radius of the big circle is capital R, and the radius of the small circle is small r, and the difference between their radiuses is capital R minus small r. So equation number 4 is the implementation of rule number 5 in our two circles, that Q equation number 4 states that QP, that is the distance between the centers of these circles, is equal to capital R minus small r. Here we will add to this equality small r, and we will get that capital R equals to QP plus small r. Okay, so we got that capital R equals to PQ plus small r. But we have equation number 1 that according to equation number 1, capital R equals to 6.5 plus small r. Okay, so we have here equation number 4 and equation number 1 that are both of them are expressions for the same radius, the radius of the big circle. So therefore, because they are both the expressions, different expressions for the same radius, they are of course are equal to each other. So we can write down equation number 5 that states that the radius of the big circle according to equation number 1 equals to the radius of the same big circle according to equation number 4. Okay, so equation number 5 actually states that capital R equals to capital R, or the radius of the big circle according to equation number 1, that is capital 6.5 plus small r, equals to the radius of the big circle according to equation number 4, that is QP plus small r. So here we have r in this side of the equation, we have r on the other side of the equation, so we can cancel r. After we cancel the r, we got that PQ equals to 6.5 units. Okay. So we found out the value of PQ, that is actually also the distance between the centers of the two circles, and we have already found out that x equals to 2.5 units. Okay, so we actually found out the values of PQ and X. Okay, so in the next step we will connect together points Q and P by a straight line. So actually here we have a rectangle QPM is a right rectangle because angle QMP is a right angle, therefore triangle QMP is a right triangle. So I'll write it down that triangle QMP is a right triangle. Okay. So triangle QMP is a right triangle. Therefore, we can implement the Pythagorean theorem in the right triangle QMP. Okay. So what is the Pythagorean theorem? The Pythagorean theorem states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle QMP, the square of the hypotenuse is PQ square. Equals to the sum of the squares of the perpendiculars equals to QM square plus PM square. So according to the Pythagorean theorem, PQ square equals to MQ square plus PM square. But we have already found out that PQ equals to 6.5 units and QM, that is X, equals to 2.5 units. And PM equals to X, that equals to 2.5 units. And PQ equals to 6.5 units. And QM is the radius of the small circle. So PQ square is 6.5 square equals to 2.5 square. PM is 2.5 and QM is R square. QM is R, so QM square is R square. So in total we got that 6.5 square equals to 2.5 square plus R square. 6.5 square is 42.25 and 2.5 square is 6.25. So I will write it down. So we got that 42.25 equals to 6.25 plus small r square. Here we can subtract 6.25 from this equality. We'll get that 42.25 minus 6.25 is 36. 36 equals to r square. Okay, 36 equals to r square. So here we will take a root out of this equality and we will get that r equals to the root of 36. The root of 36 is 6. So in total we got that the radius of the small square equals to 6 units. Okay. So the answer to the question is that the radius of this small circle equals to 6.5 units, so small r equals to 6.5 units. The radius of the small circle equals to 6 units, or small r equals to 6 units. Again, the radius of this circle equals to 6 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we have here two circles that have internal length between them at point N, that is to say they touch each other internally at point N, and we also know that AC equals to 9 units and dB equals to 4 units. Here we have right angles, and here also we have right angle, and we also have, we know that AB is the diameter of the big circle. That is to say, it equals to 2 times the radius of the big circle. And we also have 3 tangents to the small circle. This is the first one, this is the second one, and this is the third one. We actually drew 3 radiuses to this circle. Those 3 radiuses touch the line points. These 3 radiuses touch the launch points of the circle. This is the first launch point that the radius touches. This is the second launch point that this radius touches, and this is Z is the third launch point that this radius touches. Okay, we have rule number 1. According to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. So here we have radius that is drawn to the launch point and touches the launch point. Therefore, according to rule number 1, this radius is perpendicular to the tangent, or this is a right angle. And also we have here a radius that touches the launch point, that is to say, it touches point S. So this radius is drawn to the launch point. So according to rule number 1, this angle is a right angle. And also we have the third radius that touches the launch point. It is actually drawn to the launch point. For that reason, this is a right angle, and this angle is also a right angle. Okay, so actually, if we focus on quadrilateral QZMD, this quadrilateral has 3 right angles, 1, 2, and 3, or 1, 1, 2, and 3, and the sum of those 3 right angles is 90 times 3 is 270 units. It's 270 degrees. So the sum of the 3 angles of this quadrilateral is 270 degrees, and we have rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. So actually we know that the sum of those 4 angles must be equal to 360 degrees according to rule number 2. So we know that the sum of the 3 angles is 270 degrees, plus the size of the 4th angle must be equal to 360 degrees according to rule number 2. So here we subtracted 270 degrees from this equality, and we got that y equals to 90 degrees. That is to say, the size of the 4th angle is 90 degrees. Okay, so actually we have here a quadrilateral with 4 right angles, and according to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. So this quadrilateral QZMD that has 4 right angles is a rectangle according to rule number 3. Okay? But we have also rule number 4 that states that the opposite sides of a rectangle are equal to each other. So according to rule number 4, QZ equals to MD. Okay? The opposite sides of a rectangle are equal to each other, so QZ is opposite to MD, and therefore according to rule number 4, QZ equals to MD. But we know that QZ is the radius of the small circle, So we can write here that Qz equals to small r. So from this equality we can derive that dm equals to r, or md equals to r. So we found out that md equals to small r, and we have the second quadrilateral QSMC that also has 3 right angles, so the fourth angle must be also equal to 90 degrees according to rule number 2. And because of the fact that this quadrilateral has 4 right angles, according to rule number 3, it must be a rectangle. And according to rule number 4, the opposite sides of a rectangle are equal to each other. So QS equals to CM. But we know that QS equals to small r, and CM equals to QS. So CM also must be equal to small r. Okay? So then we defined PM as x, and CP will be equal to CM minus PM, that is to say CP equals to CM, that is small r, minus PM, that is x. So CP equals to small r minus x. And we created 2 equations for the radius of the big circle, capital R. The first equation states that AP equals to capital R. That is the first equation, and the second equation states that PB equals to capital R. Because of the fact that P is the center of the big circle, then PB is the radius of the big circle. Okay, so we have here 2 equations for the same radius, and we return to equation number 1 that states that AP equals to capital R. What is the value of AP? AP equals to AC plus CP, and AC equals to 9 units, and CP equals to small r minus x. So in total, AP that equals to capital R, it equals to 9 plus r minus x, or AP that equals to r, or actually r. We can write only r, that capital R equals to 9 plus small r minus x. Okay, so this is the first expression for the radius of the big circle, and then we have the second expression for the radius of the big circle, that is PB equals to capital R. PB equals to capital R, but what is the value of PB? PB equals to PM plus MD plus DB, and PM equals to X, MD equals to small r, and DB equals to 4. So in total we got that capital R that equals to PM plus MD plus DB equals to X plus small r plus 4. Or the second equation for the radius of the big circle is capital R equals to X plus small r plus 4. So we have 2 expressions for the radius of the big circle. We can compare equation number 1 to equation number 2 and create equation number 3 that states that the radius of the big circle according to equation number 1 must be equal to the radius of the big circle according to equation number 2, because it is the same radius. Okay, that is equation number 3. So from equation number 3 we got that x equals to 2.5 units, and we have equation number 1 that states that capital R equals to 9 plus r minus x. So we can substitute x in equation number 1 by 2.5 units. We substituted x by 2.5 units, and we got that capital R equals to 6.5 plus small r, and we already know that x equals to 2.5 units. Then I presented rule number 5, and we implemented rule number 5 in our 2 circles. According to rule number 5, If two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So actually, if two circles touch each other internally, then the distance between their centers equals to the difference between their radiuses. So we can implement rule number 5 in our two circles, because here we have two circles with an internal length between them at point N. That is to say, they touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, that is QP, must be equal to capital R minus small r. That is the difference between their radiuses. QP equals to capital R minus small r. That is the implementation of rule number 5 on our two circles. So from equation number 4, we got that capital R equals to QP plus small r, and we have already found out, according to equation number 1, that capital R equals to 6.5 plus small r. So we have two expressions for the same radius. We can compare those two expressions and create equation number 5 that states that the radius of the big circle, according to equation number 1, must be equal to the radius of the big circle according to equation number 4. We compared those two expressions and we got that QP equals to 6.5 units and X, we already found out that X equals to 2.5 units. Okay, then we connected together points Q and P by a straight line and created triangle QMP. Triangle QMP is a right triangle because angle QMP is a right angle. So in triangle QMP, we can implement the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PQ square equals to QM square plus PM square. That is the implementation of the Pythagorean theorem in triangle, the right triangle QMP. PQ square equals to QM square plus PM square. We know that PQ equals to 6.5 units and QM that equals to X equals to 3.5 units. On the PM equals to X equals to 2.5 units, and the only missing variable here is QM, that is the radius of the circle. So we put the data inside this equality and we found out that the radius of the small circle equals to 6 units. Again, the answer to the question is that the radius of this small circle, that is to say small r, equals to 6 units. Okay, thank you very much.